macroscopic regions that covers the entire sample in this very regular manner. So it can alter the electronic properties in a global fashion and not just in a localized fashion here. And this was something that this resulting periodic field that we get that alternates throughout the whole sample actually we realized that it's actually much more realistic to have a periodic field like this instead of what one might imagine as, being the first field that one thinks of would be a uniform magnetic field. But a uniform magnetic field would actually require a diverging gauge potential, and this would imply a strain field that diverges at the boundary, which is clearly unrealistic to expect in a real system. So this is nice that our system, allows all of these nice properties. And so, having said that, we can then go ahead and look at what the resulting electronic properties of the system are. No surprise, we get Landau levels, and then we can then look at whether some of the consequences, what some of the properties of this are. So, what will we expect heuristically? When the dislocation array varies on scales that are larger than the magnetic length, then we would still expect the formation of local Landau levels. And since this is true in our case, since from our estimates we do get a fairly large magnetic field, then we can still use this local Landau level approximation, in which now here then we will expect for the energy level spacing to depend on a local field strength. So since our field is varying, we also get an energy level that's varying. And the nice thing about Dirac fermions, as Vidya pointed out also, is that the zero Landau level is always at zero energy, regardless of the field strength. So then even as our energy level spacing varies, however, we still will have always extensive, we will always will have states at zero energy, and this gives rise to an extensive degeneracy of states at zero energy. And we can put this, we can then calculate this by adding a periodic field into a Dirac Hamiltonian, and then a sinusoidal field. And here we do see, as we expect, absolutely that we get a flat band in the direction of this periodicity, and in the transverse direction it is flat, close to the Dirac cone, and then there is a dispersion away from that, which you would expect since there are regions of transition between the regions of large magnetic field. And there are two flat bands which correspond to the regions of positive and negative fields, as we have seen, and we do see that the higher Landau levels are separated from the zero Landau level by a decent band gap. There was a picture in momentum space, and we can then plot the density of states in real space, and we do see that as expected, we do see a large density of states at zero energy. And further, that there are dispersive states at the transition regions, which correspond to the chiral snake states of the zero Landau level. And this is the half conductance that one would expect for the zero Landau level of the Dirac fermion. And in fact, so in each transition region, one gets a half a conductance coming, let's say, from a region of positive field, for example. And in this one, it would be a region of negative field, so then there would be half a conductance in the other direction. So this would add up to the chiral snake state in these transition regions. So if we add the corresponding edge states from the perpendicular direction, from the transverse direction of the other mirror axis, then we do get this grid of snake states. And at the same time, like, all of this is still physics just from two of the valleys, and if we take physics from all four of the valleys, and so the time reverse physics as well from the other two valleys, that would basically be this picture, but then we add another of this, but flipped over, so the time reverse physics, and they jointly give helical snake space. Yes? this safe phase is a term that came out in a paper of Patrick and some others about 15 years ago, in which they had a different model, but in their model they had regions also a sort of positive and negative field. And the idea is that since these are edge states, so there is this idea of curving around these individual regions. So they sort of curve, and yeah. And so given this large density of states at zero energy, we can then look at what kinds of physics we might expect from this large density of states. And a large density of states tends to enhance expression effects and can favor superconductivity. If we estimate the carrier density in the flat band, we find that it's pretty high, and so one can reasonably expect the Fermi energy to be in the flat band or close to the flat band. And if we revisit the BCS neutral gap equation, we find that the flat band limit gives a pretty different result. So this is our typical result for a Fermi surface, in which the gap depends, it varies exponentially on the interaction strength and the density of states. It's a familiar result. And if you just take a limit of a completely flat band, we see that instead it depends parametrically on the interaction strength and the flat band degeneracy. This is a pretty different a pretty different prediction of what we might expect. So that is that is our prediction of the electronic properties in this model, and now we can look at how consistent it is with the experimental data. So the superconductivity has been measured in several multi-layer systems with a range of TCs, but the individual constituents, they look at single films who go in exactly the same condition. We find that they do not superconduct above 0.2 Kelvin. Further, the superconductivity is two-dimensional, as evidenced by the anisotropy of the upper-critical field, which points to it being close to the region of the interface. And then tellingly, that at least one of the materials needs to be a narrow gap semiconductor, so that if both materials are made of wide gap semiconductors, the resulting bilayer does not superconduct above 1.5 Kelvin. And this points to the importance of band inversion as being related to superconductivity. And more than band inversion, one actually needs a regular dislocation array, because samples that do not have a regular dislocation array, let's say if you have sort of puddles of dislocations that can happen without them joining up to become a regular array, then they only show partial superconducting transitions. This is the most interesting experimental evidence in these works, in which they have many different bilayers which have different array periods, dislocation array periods, and they see that as the dislocation array period decreases, that TC increases from 3 to 6 Kelvin. And this is consistent with our theory, because in our theory, as the dislocations are closer together, since the strain is strongest around the dislocations, then we also expect an increased flat band degeneracy when the dislocations are closer together. And this, of course, will saturate at a certain point, because when the dislocations are too close, then the field varies on length scales that are too short, and then this also will destroy this local Randall level approximation. So this strong increase from 3 to 6 Kelvin is consistent with the TC depending parametrically on a flat band degeneracy, and it's pretty atypical. There are other possible experimental verifications that can be done also. the disk group is clearly paving the way in some of these things, and there remain other things that can be seen as well. For example, density of states. Is it possible to see a level spectrum, for instance? And in some of these superconducting